This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, good morning everyone. So today's lecture, this morning lecture, is the last one where we would present new material. So robustness analysis is like a crown achievement of this subject. So you will see the power of frequency domain analysis methods, and you can really understand how powerful they are in addressing robustness analysis. So this afternoon I will present like a shorter lecture. The idea is first to wrap up the whole subject, just sort of go through what we've done. I will then talk about consultation times leading to exam and also the exam itself. So just give you some sort of idea of what to expect. So that lecture will be shorter, and it will be really a goodbye lecture. I will see you at the exam, because next week Jane would be just solving exams. So I think she would do those tutorial style questions for 2 classes, and then she will be doing for a couple of classes exam style questions, right? So that's a good preparation for the exam. All right, so robustness analysis. First I'll motivate things a bit, then I will talk about how to abstract or mathematically model perturbations in your control loop. This is a very important first step in the analysis. And then we will present the so-called small game theorem. Small game theorem is a really important result in control theory. It has a range of different versions. You will see only one version that is sort of consistent with frequency domain methods, but you have no many generalizations of this result. It is the most useful, I would say, result when studying robustness. And then we will also talk in the end about performance robustness. We won't go into too much detail. I just want to sort of indicate just how powerful these methods are. So not just for robustness, but also robust performance. Because if you set out to achieve certain performance objectives, the question is, well, how do they be affected if there is any perturbation in the plan? Right? So that leads to the notion of robust performance. So we will present some tools that you can use to address this as well. And then we will wrap up. So a common sense thing which you should be sort of all comfortable with is that no model would be exactly describing your system. Right? So there will be always an error between the model and the true plan. Right? So obviously the question, an important question is, if we design a controller based on an incorrect model, would the same controller perform well when applied on the true plant? Right? Because you have one controller that needs to stabilize both the model and the plant. The only thing we know is the model, right? So you do your best you can to make the model as good as possible, as high fidelity or as useful as possible. But then your design is solely based on the model, right? And then when you implement it on the true plan, the question is, would it still work? Now that leads to question of robustness, right? How much of the perturbation in the plant can you cope with before you lose stability? That's the question of robustness. And the other question is, well, how does perturbation affect your performance? This is a question of robust performance. So both questions are important, and they are addressed in this lecture. So here is, the general setting that we are dealing with in this lecture. So first you have a model. So this nominal transfer function is your model, and you design controller C based on the model. But then the question is, how will the same controller perform on the real system? When I use the same controller, right, on the true system, now I have the actual transfer function G. Right? So know that G, the actual transfer function for the true system, right, is different from the model. Always. You can never expect them to be the same. Right? I mean, this is still under the assumption that the true system's model can be described by some transfer function, that the model is linear. But in general, the model is actually non-linear, so there will be even more perturbations, non-linear perturbations, that cannot be captured by just transfer functions. In this lecture, however, we concentrate only on the case when, the plant is assumed to be linear, right? So it can be modeled by some transfer function, and the model is also linear, right? But more generally, you can pose a question of robustness when the plant is non-linear. We won't address that in this lecture. All right, so the first thing is, well, how do I model the mismatch between G and G0? You can do it in different ways. Mathematically, you can do it in different ways. And each different way may have its own advantages in terms of analysis and design. So we will go through some of these modeling sort of issues first. But first, to really understand what we're doing here, it's useful to go through these comments. So what we need to do in the robustness analysis is not just whether the controller would stabilize the true plant. It's useful to actually know the amount of mismatch between the true plant and the model that we can cope with, right? So before we sort of lose stability and performance. So what we want to characterize in robustness analysis, how much different can G be from G0 before this guy loses stability properties and performance that we wanted. So we will relate this actual model to the nominal model, and it can be different. It can be done in different ways depending on the type of modeling errors. Well, for a linear time invariant modeling errors, we consider additive and multiplicative modeling error models, and we will go through both. So first, I will present an example. So when you buy a resistor, right? So you go to a shop and you buy a resistor. Well, if the resistor is, I don't know, 1 ohm or 100 ohm, you buy a 100 ohm resistor. But when you read the specifications, the manufacturer would guarantee that resistor is in some range. Resistance is in some range. They would never sell you a resistor which is exactly 100 ohm. So the specifications would just say, well, maybe, what they guarantee is that resistance will be somewhere in the range between 99 and 101, right? For instance, right? So what is common to do is, it's common to say, well, most of the time, on average, resistance would be 100 ohms. So I will use 100 ohm as my nominal model for this resistor, right? But the true model is anywhere between 99 and 101. So in other words, the error between the two is plus minus 1 ohm. Right? Now, what you need to do is, when you're designing systems, by the way, your system might be an electrical circuit that consists of lots of capacitances, resistances, inductances, and each of these elements may have its own sort of errors that you need to cope with. So typically you would use the nominal value that the manufacturer tells you, well, that's the value roughly, right? And then you would need to sort of cope still with this uncertainty, which if the manufacturer is good, they would really guarantee, and the true resistances would be in this range, right? The errors would be within this range. So now we want to talk about, okay, how do we represent these sort of errors in different ways? So we will present two ways of doing it. So what I'm giving you here is I have a resistor with resistance R, and then R0 is the nominal resistance. So think of R0 as 100 ohm, and R is some unknown resistance in this interval between 99 and 101. You can think about it this way. So one way to represent it, this is the simple way we can say, well, R is R0 plus R epsilon. So this is sometimes called additive error model, and that's one way to represent it. Now you may say, well, that's probably enough. Well, it turns out that in many control analysis and design sort of techniques, it's also sometimes useful to represent this error in this way. So know that now I'm representing, the true resistance is R0, the nominal resistance, 1 plus this R delta, where this R delta will be the amount of multiplicative error. It's just a different way of doing it. I presented both the formulas and block diagrams for both additive and multiplicative for the simple case of resistance, right? But you can generalize the same thing when instead of R, you have more general transfer function G of S, G0 of S, right? So R will be G of S and R0 will be G0 of S. So you can still represent any arbitrary transfer function, not just static models like this. This is a static model, no dynamics, right? So, but you can generalize this to more general transfer functions, and then the additive error would be really like, okay, you represent the true transfer function G as G0 plus G epsilon. So basically, this is the formula, right? And coming from resistor example, it's clear where this comes from, right? And you can also represent it using multiplicative error, where now your true transfer function is G0 times 1 plus G delta, where G delta is the sort of amount of multiplicative error. You may ask, well, why both, as I said, different techniques might benefit from one or the other, right? So we won't actually go into details, but I just want to give you these examples so simply that you are aware of it. It's useful to also consider a couple of relationships. So if you just look at the algebraic equations for G epsilon and G delta, you will see that G epsilon is just G delta times G0, and also in resistor example, this is easily checked. Right? So there is a relationship between multiplicative error R delta and additive error R epsilon. We will now go through several examples. What I want to do is I want to present more complicated examples than this. This is very simple because the system is static. But I want to present you examples when you have some transfer functions really, and I will plot body diagrams for various, transfer function, in particular, G epsilon and G delta, for a range of different examples, just so that you get sort of some intuition behind how general these things can be, right? Depending on the system, these things can become quite general. All right, so here is one example. By the way, type 0 systems, I did not formally introduce them, but if you read Ogata, he introduces these systems. These are the systems where the transfer function doesn't have an integrator. Type 1 systems are the systems that have a single integrator in the transfer function. So here you don't have an integrator, so this is type 0 system. So G0 here is plotted, so this is I'm just plotting the magnitude plots for the nominal transfer function G0, and I'm saying now, okay, if my true transfer function is G1 or G2, I want to plot the additive errors between G1 and G0 or G2 and G0. So these are the G epsilon 1 and G epsilon 2, or multiplicative errors corresponding to the same sort of differences. So note, if G0 is plotted there with red, the magnitude plot, so that's for this transfer function, then multiplicative and additive errors for G1 versus G0 are given by green. G epsilon 1, that's the additive error, magnitude plot, and G delta 1 is the multiplicative error, magnitude plots only. If we consider G2, then the errors are given by blue. So G epsilon 2 is the additive error, and G delta 2 is the multiplicative error. So look, this is actually not such a bad sort of situations. You will see when we go through further examples, things can become very messy in terms of the types of perturbations. These sort of plots. By the way, G epsilon 1 and G epsilon 2, or G delta 1 and G delta 2, are basically the amounts of perturbations in this example. And typically the analysis would be, well, if I analyze, if I design controller C so that the closed loop system, when G delta is 0, if that system, which is nominal system, well, if G delta is 0, that's the nominal system. Yeah? Everyone can see that? So if that system, nominal system, is stable and satisfies some performance, then the question is how big, this G delta is allowed to be before we lose stability or we lose some performance. So obviously then the magnitude, plots of this guy and frequency, well, phase is also important, but robustness that we will present, robustness tools that we will present will only use magnitude of these perturbations. Similarly, when you look at this diagram here, the nominal system here is when G epsilon is 0. So then if you design the controller when G epsilon is 0, the question is how much of G epsilon, right, magnitude can you cope with before you lose the stability and performance. Yep.
Why are we going up to the phase?
So can you repeat that?
You said only the magnitude. Why we don't?
I will present small gain theorem, right? So there are some results that can look at phase that's beyond the scope of this subject. So small gain theorem only uses the magnitude. It's a sufficient condition, but it's rather powerful. We will see later on when we present it. Here's another example. This is a type 1 system. The story is the same, except now we have that the nominal system has an integrator, so it's a type 1 system. There is one integrator, that's type 1 system. And then again, if the true plant model is G1, then the errors are represented in green, and if the plant model is G2, then the errors are represented by blue. So again, this is just to give you some idea of how magnitudes may change, as we change, the models. By the way, note that the difference between the nominal model here and the true model here is just in the location of this pole, right? So this is exactly the same in the two models. There is only difference in a single pole, because this is different. Everything else is the same, right? So, and then this is what you may get for the G epsilon and G delta magnitude plots. Now, this is a very interesting, different example. What this example tells you, suppose that your nominal model, G0, is assumed to be without time delay. But suppose then that you have some time delay in the true system. So note that both G1 and G2 have some time delay. This exponential here corresponds to the time delay. Right? So you can see, these sort of multiple peaks, resonances due to the neglected time delay. You need to basically be able to stabilize the system, right? So the idea is, I just want to go back so that you understand what we are doing here. Suppose I stabilize this system when G delta was 0. Now the question is, when G delta now has some of these characteristics, like G delta 1 or G delta 2, magnitude characteristics, would I still be stable? That would be the question we would be asking. And small gain theorem would answer this question for us. Okay. So look at this mess. I mean, if you, by the way, when you look at multiplicative disturbances, there are a number of resonance peaks that you need to deal with, that you're basically neglecting. In the design, you are assuming that G delta 1, G delta 2 is 0, right? That's in the design because you are using the non-delayed plant. But then what you need to cope with or be robust to is basically this sort of multiplicative perturbations that have all these resonance peaks. These resonance peaks are very nasty, very hard to deal with. So neglecting delay would be, you know, a sort of a tricky thing. And you can see this from this sort of magnitude plots. Once we present also the small gain theorem, you will be able then to relate, you know, just how these sort of, which ones of these can be coped with and which ones cannot be coped with. We cannot conclude if you cannot cope with it. So small gain theorem is a sufficient condition. So if the small gain condition does not hold, you might still have stability, right? So, but you can definitely pick out the ones that you can cope with. All right, so we want to now talk about robustness of stability. So this is the setup for the small gain theorem. So we have a nominal transfer function, and the controller was designed so that this closed loop is stable, right? And then we want to apply the same controller so that this closed loop system with actual transfer function is still stable. So the question would be, well, what would be the condition that would guarantee stability of this system, right? So that's the question we are asking. We assume, so what we will assume is that both lambda 0 and lambda have the same number of right half plane poles. So open loop transfer functions have the same number of unstable poles. So you can assume, you can achieve this when either G epsilon or G delta are stable, right? When they are stable, then this condition would hold, right? Can you see that? Because it's you know, what are the poles, let's say, of G versus G0, right? So, well, this guy would have poles which are union of that guy and that guy, right? So if G epsilon is stable, then we are not adding any unstable poles for the plant, right? Obviously controller is the same. Controller doesn't change anything, right? The only difference in number of poles can come from difference in the plant models between G0 and G, right? So this is an assumption we'll use. Can everyone see this? Right? So if G epsilon is stable, then obviously, and G was, let's say, assumed stable, or look, G0 has certain number of unstable poles, right? Let's say 5. Right? Then if this is stable, then this would also have 5 unstable poles. And then if controller has 2 unstable poles, then the difference between poles, unstable poles for lambda 0 and lambda, there's no difference. Because now G has the same number of unstable poles, and C is the same for both, right? So that cannot change the number of unstable poles. So this is an assumption that we will use, which applies for stable perturbations. So here is the small gain theorem. So I will first state it, and then I will explain the intuition behind the proof. So what this says is, if you now plot either, let's say, well, know that this is a function that depends on omega, right? And this inequality we want to hold, we want it to hold for all omega, right? So we want this inequality to hold for all omega. So what you have here is know that there is a magnitude of the additive perturbation, or here we have a magnitude of the multiplicative perturbation. And here lambda 0 and C are all known. This is all coming from the nominal model. So this term here comes from the nominal model, and this comes from the perturbation itself. This again comes only from the nominal model because lambda 0 is really G0 times C. Right? And C is also coming from the nominal model. So all of these things we would know in the design, and then we can estimate how much magnitude we can cope with in perturbations, right? We can provide a bound on the magnitude of the perturbations that still guarantees stability. All right. Can everyone see that? So if I take, so suppose I take this is a function of omega. I take it on the right-hand side, then I have 1 divided by all of these, but this is a function of omega. Then I'm saying if my perturbation, multiplicative perturbation magnitude is smaller than this known function, this is a known function because I know my normal model. For all omega, then I have robust stability. I still have stability, right? I still have stability. Now, where does this inequality, come from? So this is actually a very cool interpretation of the small gain theorem here on this picture. So what's plotted here? The full blue is the nominal open loop gain Nyquist plot, and the dashed is the true open loop gain Nyquist plot. So lambda is really G times C, and lambda 0 is G0 times C. Right. So we plotted them. Now, for any given, by the way, on both of these curves, right, omega is a parameter. As we change omega, we get different points on these two plots. Suppose that we consider one particular value of omega, I call it here omega bar. So the point that corresponds to omega bar on lambda 0 plot is here, right? And the point that corresponds to omega bar on the dashed line is given here, right? So now what you are saying is, well, what is the geometrically, what are different sort of distances here, right? Well, the distance of this point from the critical point is really norm of 1 plus lambda 0 evaluated at omega bar. And then the distance here, you can show that it's really G epsilon C, or which is the same as G delta on the 0. We are now using the relationship between G epsilon and G delta. So what does it mean then that, this whole thing is, so this product is smaller than 1? Well, it means that this guy here in the denominator is larger than the product of these guys in the numerator. But what does this geometrically mean? Well, it means that this distance from the critical point is larger than this distance between the two plots. So what this means is, that the true Nyquist plot will stay within these circles. You know that there are these different circles that are plotted, which are telling you basically, the distance between so basically the value of the lambda 0 at different omegas and lambda at the same values of omega. So if you are now basically ensuring that for all frequencies, this radius is always strictly larger than this radius, then the dashed line would never encircle the critical point. You will have exactly the same number of encirclements for the two plots. So in other words, the dashed line is staying in a neighborhood which is strictly smaller than the distance of this true plot, blue plot, from the critical point. So you can never have a different number of encirclements by the dashed plot and the true blue plot. Does this make sense? Are there any questions? Yep.
If I have unstable electricity, I need to cross -180.
You need to encircle.
I need to encircle.
Yes.
So how can I apply that?
So by the way, in the small gain theorem, what we started with is an assumption that lambda and lambda 0 have the same number. of unstable poles. So since lambda 0 has, let's say, 5 poles, unstable poles, then we will have to have 5 encirclements, right? To kill this sort of 5 unstable poles for stability, right? Because we want z equals 0 in the Nyquist criteria, so p is equal minus n. Right? So we need to satisfy this criteria. So we will have certain encirclements by the full loop plot to have stability. So the small gain condition just guarantees that the dashed plot, the true open loop gain, would always stay in the neighborhood of the full blue plot, full sort of line, which is smaller than the distance from the critical point. So that, you know, these concentric, these circles here, dashed circles here, are showing you these different neighborhoods, and the dashed plot would always have to be within this sort of dashed circle. So you can sort of say, if you look at the envelope on both sides of these circles, you plot all these circles and you put an envelope around them. So this is like a boundary that touches all these circles. Then you know that if the small condition holds, then the true Nyquist plot for the true plant, right, for the true plant, would be in that sort of neighborhood of the nominal Nyquist plot. And the small gain condition simply guarantees that this neighborhood would never sort of cross the critical point, will touch the critical point. And so that from there you conclude you would have exactly the same number of encirclements on the critical point. So the true plant Nyquist plot lambda or J omega will have then the same number of encirclements as the dashed one, if the small gain condition holds. Does that make sense?
Yes, but for some frequencies, I already encircle minus 1, so the magnitude that became margin is already minus for some frequencies.
No. Wait. For stability, right? So for stability, when you have an open loop transfer function that is unstable, in order to have stability of the closed loop, you have to have encirclements. So a small gain condition simply guarantees that the number of encirclements will not change. So that it will be the same for the nominal and the true Nyquist plots. So note that here we only use the magnitude information to conclude stability, but you know, in general, phase also affects things. This is a sufficient condition. So this is a sufficient condition. Still very powerful, right? So just a few comments which I already mentioned. So a small gain condition ensures that the number of encirclements of the critical point minus 1 J0 by the nominal Nyquist plot does not change when the Nyquist plot is perturbed by the modeling error. In other words, you have the same number of encirclements for the true system's Nyquist plot and for the nominal system's Nyquist plots. Right? It's only sufficient and potentially conservative. You know, if this condition does not hold, the system may still be stable. So if the condition does not hold, the system may still be stable. It is, you know, very hard to obtain a better, sort of less conservative condition if you only concentrate on magnitude. So without any phase information. So small gain condition is pretty much as good as you can get just by looking at magnitude. And the results can be extended to unstable perturbations. It's beyond the scope of this subject, so I will just sort of mention that you do not need to, it's not necessary to assume stability, but you can deal with instability, but it just complicates things. All right, so I also want to, so if there are no further questions, I just want to stop. If you want me to go back and talk about anything else. explain? No? All right, so let's just go through robustness of performance. So note that one way to capture performance of your system is to require certain properties of these sensitivity functions. Now, if we use a nominal model, nominal transfer function, to design the controller, then we can talk about nominal sensitivity functions. They are all calculated with the nominal model G0. Obviously, when we have some perturbations, the question is, well, how would this affect the achieved transfer function, sensitivity transfer functions? So here is the picture now. When we apply the same controller on the actual system, then we get so-called achieved sensitivity functions. So these are calculated with G instead of G0. So obviously you design a controller trying to shape or, you know, get some properties, nice properties of these guys, and then you take the same controller, you plug it into that closed loop, and then you get achieved sensitivity transfer functions. So obviously what we are in the end interested in are the achieved ones, right? Because that's what will determine how your system performs in practice when you implement it, right? So we can, you know, rewrite the multiplicative error in this way, and suppose that the controller CS achieves these nominal sensitivities. Then you can really do just some algebraic calculations to say, well, achieved sensitivity functions are given here, but now everything depends on this G delta, which is the multiplicative perturbation, but also everything depends on this S sub delta, which is basically a new object. So if we define this object, which is, you know, 1 over 1 plus T0 is the nominal complementary sensitivity. This is calculated with the nominal controller, sorry, nominal model, Planck model, and G delta is the multiplicative perturbation. So basically, we have these relationships between achieved sensitivities on the left-hand side and the nominal sensitivities on the right-hand side, but the relationship involves multiplicative error G delta and also this error sensitivity S sub delta. So now, if you use this, all these formulas are just simple algebraic calculations. You look at what these guys are, you look at what these guys are, and you use the definition of G delta there. Right? So then you can just rewrite algebraically everything in this way. So you can conclude some things. So, for instance, well, this is a proof. I won't go through the proof, but steps are really clear so that you can see how, you know, you can relate sensitivity to nominal sensitivity. So note that sensitivity on top is really achieved sensitivity S is S0 times S delta. And the steps of showing that are given here. So this is just what I told you, it's just algebra. With all the definitions we used, you just have some algebraic steps that make this relationship hold. But one thing is that, note, if S delta is roughly, you know, 1 plus J0, so it's roughly 1, then, you know, you will have that nominal and achieved performance are similar. Why is that? Well, look at the formulas here. Each of these, you know, are, you know, multiplied by S delta, and you know, when these guys, you know, close to 0, these guys will be quite similar. By the way, S delta, you know, being close to 1 would require really G delta to be close to 0, right? So in any case, if you have that condition, then there will be little difference between, let's say, S0 and S. Because if S delta is roughly 1, then S is roughly S0. Does that make sense? Yeah. So now this is roughly true if you have that this condition holds. So for instance, when G delta is 0, this condition definitely holds. right? When there is no, when G delta is 0, then this definitely holds. So you can see G delta 0 would imply something like this, and that implies that achieved and nominal sensitivities are almost the same. So this is the sort of condition that you would like to have in order to guarantee that what you design a controller for, the nominal sensitivities, would then imply similar things for your true system. Now, are there any questions regarding, so this is it. I don't want to present any more proofs or anything. This is just giving you some intuition. You know a lot of frequency domain analysis tools, and this is just giving you an extra insight into how powerful these frequency domain methods are. Questions? All right. By the way, this is the most complicated thing in the subject, probably, because it brings everything together, right? So I don't expect you all to understand it. I mean, I'm doing my best, but I don't expect you to understand it from the first go. But I will have a few consultations before the exam, so you're definitely very welcome to come and see me. All right. What I want to do now is just present an example to demonstrate just how much you can learn from all these frequency domain tools. So what is given here is you are given a nominal plant, G0, and you are given this controller, and by the way, typically you will be asked, okay, design a controller that achieves something. What I'm giving you here is already a controller that achieves something. So what is given here is, so what we have here is reference input. We are assuming reference inputs that are unit step. We assume input disturbance, which is sinusoidal of frequency 1. Omega is 1 here, right? And with the unknown amplitude, we don't know amplitude of this disturbance. And then we have phase multiplicative error. We have it to be smaller than this. With unknown amplitude and phase, this is phase for the sinusoidal disturbance. Amplitude is unknown, phi is unknown, and multiplicative error satisfy this inequality. So you can think of the multiplicative error being actually this thing. Know that this is stable, so I assume stable multiplicative error. So now we just want to plot various diagrams so that we can perhaps just conclude about achieved sensitivities. Note the magnitude plot of G delta T0 in decibels shows this, so it is smaller than 1 for all omega. So hence we would say roughly, this sensitivity, error sensitivity is roughly 1. You only need to look at the magnitude plot when we talk about this, right? So this is strictly than 1, and this is the sort of thing we were needing to say that achieved sensitivities are similar to the nominal sensitivities. So by the way, why I can plot this? Well, I know my G0 and C, so I know my T0, and also I gave you what G delta is, right, in this case. Here are the body diagrams. So note what's plotted here is quite a lot. So you have lambda 0 is given by red, controller is given by black, T0 by blue, G0, the plant, is by this light green or almost yellow, and SIO is given by the green. So note several things here. First, the complementary sensitivity, is close to 0 for a range of frequencies, right? So what would that mean? it means that we would have a good tracking of reference signals in this frequency range, right? Because complementary sensitivity is close to 0. For large frequencies, complementary sensitivity is much smaller than 0. That means that we can reject well the noise, measurement noise. Note that lambda 0 and C have this peak at frequency 10 to power 0, that's 1. Where does this come from? What do you think? Yes, but why would this be useful in this case? I go back to the sort of description of the problem. So you're right. So this S squared plus 1 creates that peak in lambda 0, right? But note that here we have input disturbance, which is A sine 1 times t. So frequency here is 1. So know that this controller here has internal model principal structure. So since model of this sort of disturbance is exactly S squared plus 1, right? We can generate this disturbance here with this S squared plus 1. So any internal model principal controller that's trying to reject a certain disturbance at a certain frequency would have the plots that look exactly like this, with peaks. So lambda 0 has this sort of peak going to infinity, but note what happens with the green plot. Si0 has gain 0 at frequency 1. So this sort of cusp down means actually it's 0. It actually goes to minus infinity in decimals. So what does this mean? Well, it means that our system rejects this disturbance at that frequency. So the output of the system will be not sensitive at all to that disturbance at that frequency. Right? So this sort of peaks down are typical consequence of the internal model principal controller structure. Okay? So what else can we see? Well, from these body diagrams, what's happening with the controller at high magnitude at high frequencies? The controller gain is increasing. Why would that be maybe undesirable? Well, you would typically have some noise hitting you somewhere, right? So if the controller is affected by that noise, then there will be high gain, right? Because the controller will be producing large control signals to just cope with this sort of high frequency signals. But high gain controls, high magnitudes of control signals may saturate your actuators. So when you see that magnitude of the control transfer function is large, you know, in some ranges, that means that you need large values of control signals. That means you need large actuators, I mean unless you want to saturate. Right? Because what saturation? Your system is telling you you need to supply 100 newtons, right, by your motor, and you can only supply 50. So you get stuck at 50. You can't supply. The system is asking 100, but you can only supply 50. That's a hard nonlinearity, and that can cause the instability. That itself can cause instability. All of this is done by neglecting all nonlinearities. But when you see something like that, high gain and high frequencies, that can spell trouble. Because we neglected saturation nonlinearities, but this might cause saturation. So, look, what we saw is, okay, I started talking about this. So complementary sensitivity is close to 1 in this frequency range, so we have good tracking for this range of frequencies. Disturbance rejection at frequency 1, right? We also talked about, that's the internal principle thing. So we do have good phase margin. So when you look at this controller, so these dashed lines, so this is the crossover frequency, where the red plot crosses 0, that's where we read crossover frequency. And then the frequency at that crossover frequency is given by red, right? So that's the frequency. So we do have some phase margin. This is good phase margin here, right? So what else? Sensitivity peak is small, which is good. So we do not have, look at the sensitivity function. You know, there aren't too many sort of big peaks going above 0, right? That's good. And then also when we look at the G delta that we were given, you know, times T0, that magnitude is smaller than 1 for all frequencies. So and this is also good in order to have good robust performance. So achieved sensitivities will be close to the nominal sensitivities. And I already said that high gain control might lead to saturations, and that's undesirable in general. So look, this is the sort of toolbox that you have at your disposal. So when you design your controllers using the tools from this subject, in the end you need to sort of plot your sensitivities and analyze them in the way we just did, so that you check whether your design, has any drawbacks, right? And whether you achieved all the performance specs. This example was not, given in a way where I said, design a controller. I gave you the controller, which was designed, and we were just sort of analyzing how you would assess the performance of that controller at the very end. This would be the last step in the design, right? So you plot all of these functions, and then you say, okay, are there any sort of culprits, are there any sort of suspicious, gain plots? Based on everything we've learned, you need to now apply to these plots and analyze them and understand them. If you had, let's say, some sensitivity peaks, if this green went way above 0, you might need to deal with that, right? Because that would mean that the system might amplify some input disturbances, right? At certain range of frequencies. Right? That, whether you would need to deal with it or not, depends on your application. If your application genuinely you do not expect to have disturbances in this frequency range, then you forget about it. If there would be no disturbances in that frequency range. But if you can have disturbances in that frequency range, then you have to go back and do something about it. So this sort of step will be the final step. So you do your root locus, you do your, whatever design we learned so far. You do your frequency domain tuning or PID control tuning. Then you need to plot these things in this way to really analyze in the end, okay, what did I really achieve? And if any of these things do not tick off some boxes, you need to go back to the drawing board. Okay. So, all right, so what we did today, we just considered, robustness to modeling errors, and we saw that we can represent these modeling errors in different ways, and we presented small gain theorem, which is a, theorem for ensuring stability under some perturbations. If perturbations satisfy some inequality, you will still have stability for the nominal closed-loop system. And we also presented some conditions that guarantee robust performance. So small mismatch between nominal sensitivity transfer functions and achieved sensitivity transfer functions. Okay, as I said, this is the hardest part of the whole subject. So I will, so we run out of time. I will, so next week we don't have consultations because I'm away, but then 2 weeks leading to exam, I will have 2 consultation times in each week. So you will have plenty of time to see me before the exam. I will talk about that this afternoon, right, in the lecture. Thank you.
The blood cells the circle.
So the radius is basically, you look at what is the value of lambda 0 at omega bar, that's this point, and what is the frequency of lambda at this point, that's this thing, and that's the distance between them.
Yeah, I know that this is but I can also draw a wide circle.
No, but why is this important? We want this